Okay, let's solve these problems and then we conclude this chapter, okay, with these problems. Okay, the problems as such are of course not very difficult. Note down these problems and I hope that I expect that many of these you are able to solve, okay, on your own. Okay, so note it down, solve it, get some answer, whatever comes to your mind, apply that logic, okay, do the calculations and try to get the correct answer in first attempt, okay, and then we are going to discuss it now. Okay, it's like this. Very simple one, okay, not very difficult. So half-life is given. Okay, first of all, let's write whatever is given. It is 5,000 years. 5,000 years. Okay, that's fine. Now, what is the meaning of this? X200. This is the mass number. Mass number is given. Okay. What will be activity of 50 gram of this sample? 50 gram of this sample. Which sample? This sample here. Okay. So let's find out activity. Activity is lambda times n. Okay. Now what is lambda? Lambda will be equal to ln2 over t half. Okay. This is given approximately. This is going to be 0.7 over. This becomes 5 into 10 power 3. This becomes per year. Per year. Now, the problem as such is not difficult, but when you start calculating, then the confusions okay, arise. Now, this is going to be equal to 0.14 and 10 minus 3 per year. Per year. Now, if I want to find activity, okay, so activity, okay, now what is n? What is n? Is number of nuclei or atoms. Okay, both are same. One atom has one nuclei. How many number of nuclei are present? Okay, if I have 50 gram of this sample here, this sample. Okay, so now it will be equal to number of moles. Okay, number of moles times Avogadro number. Avogadro number. Okay, so this n will be equal to number of moles. So 50 gram over 200 gram. Okay, atomic mass is not given. Okay, it is not given. So we can make use of this. Mass number, both are approximately, okay, roughly the same. Okay. So if it is not given, then I have no other way, but I have no other choice but to use this value. Okay, into 6 into 10 23. Well, I'm getting some approximate answer. Okay, so this is like 4 here and 1.5 and 10 23. What is this? What is this? This is number of atoms, number of nuclei. Okay, so here I have number of nuclei, so 1.5 and 10 23. What is this? Number of nuclei. Okay, what will be activity? A will be lambda times n. Okay, now if I use these values as such, 0.14 into 10 power minus 3 into 1.5 into 10 power 23. Okay, if I use these values, okay, that's fine, of course I can use it. But then what will be the unit? It will be per year. This is just a number, a pure number, multiplied by this value here. This is per year. So this activity I am going to find per year, which is not an SI unit. What if I want my answer in SI? Okay, this will be per year. Okay, what if I want to write my answer, I want to get my answer in SI, that is becquerel. Okay, that is decay per second. Then I will have to change this into per second. Okay, so this will be equal to 0.14 and 10 minus 3, this is per year, divided by, in 1 year I have these many seconds, okay? So 3 into 10 power 7, now this becomes per second, okay? You understand this? Okay, and then my activity will be equal to 0.14 into 10 power minus, you see this becomes 0.14 over 3 into 10 minus 10, 10 minus 10, minus 10, okay, over 3. What is this? This is lambda, okay, decay constant. And then n is this, 1.5 into 1023, okay. This becomes, you see, this becomes to 0.07 and 10, 13. Okay, so this is 7 into 10 power 11. This is per second. Per second, okay. Decay per second. Decay per second. Okay. Decay per second. So this will be becquerel. This is the activity of this sample. That's how we do it. Okay. So sometimes we have to make all these calculations. I have to find number of atoms. I make use of number of moles, relative number. And then I have to be careful with this unit. It is given per year. Half-life is per year. Half-life is 5000 years. Okay. So if I want my answer in becquerel, which is SI unit, I will have to write all the values in SI. Only then I can find answer in becquerel. Okay. So first we did. Now, second should be easy. It should be very easy. Okay. Let's see. Okay. Second one should be very easy. At t is equal to 0, the initial activity is given, half-life is given. I want to find nuclei present at t is equal to 0. Okay. Activity is given. Okay. Half-life is given. T half is equal to t naught. So what is lambda? Okay. It is ln2 over t half. It is ln2 over t naught. That's fine. Okay. Now activity A naught is equal to lambda times n naught. Okay, activity is lambda times n. Okay, initial activity lambda times initial number of nuclei or number of atoms, both are same. Okay, for an element, for a radioactive element. Okay, number of atoms, number of nuclei, both are same. For element, okay, not for the compound and all that. Okay, for element. Okay, here. So n naught. So first question is n naught, it will be equal to a naught over lambda. That's it. So a naught over lambda. So this becomes a naught t naught over ln2. That's it. That's my answer. That's my answer. Number of nuclei present and decayed after one average time. Okay. One average life. T is equal to t average. It becomes 1 over lambda. Okay. So n will be equal to n naught. N is n naught. Okay. E power minus lambda times 1 over lambda. Okay. This becomes n naught over E. Okay. Do you understand this? So this is what is this? This is number present. Number present. Okay. N. This is equal to n naught. Okay. So a naught t naught over E ln2. Okay, that because only a naught and t naught are given. Okay, n naught is not given. Now number decayed, and d is initial number minus number present. Okay, so this I can take out. Okay, it is a naught t naught over ln2. This is common. N naught minus 1 minus 1 over E. Okay, that's it. That is the number of nuclei present and decayed after one average life. One average life is 1 over lambda. Okay. Now, number of nuclei decayed between t is equal to t1. Okay, so this is going to be a little confusing. Okay. Now, how many nuclei have decayed between T1 and T2? Okay, the third question. Okay, number decayed okay, between t is equal to t1 to t is equal to t2. Now how did you find it? Okay, what answer did you get? Let's see. This will be equal to number present at t1, okay, minus number present at t2. Okay, did you do it same way? That's how we can do it simply. Okay, so this n, let me write it another value. Let me write it as the small n, just to avoid confusion. This will be equal to number present at t1 minus number present at t2. Okay, so this will be equal to n naught e minus lambda t1 minus n naught e minus lambda t2. That's it. I already know lambda. I know n naught. Okay, what was n naught? N naught was a naught t naught over ln2. That's it. This was n naught. Okay, and then e power minus, okay, lambda. What is lambda? ln2. Okay, so t1 ln2 over t naught, that is lambda, okay, minus e minus t2 ln2 over t naught. Okay. That is one answer. Okay. Now, it is not necessary that in your options the answers are given in this form. You see, this is absolutely correct answer. It will match one of the options if the answers are given in this form. Now, the same answer can be given in a different form also. Let's look at that. That is also very important. Okay. So now, I can write this as equal to n naught half power t1 over t naught. Okay, number of half-lives. Okay, minus n naught half power t2 over t naught. It can also be written in this manner, and you have to be careful. Okay, now this is going to be equal to n naught. What is n naught? It is a naught t naught over ln2. This was our n naught. This we calculated in the beginning. Okay, and this is going to be equal to half. Okay, so half power this, so it becomes 2 power minus. Okay, you see half power 3. It is same as 2 power minus 3. Both are same. So I'm writing it this way. Okay, it is t1 here, t1 and t naught over t naught minus 2 power minus t2 over t naught. Okay, see, both are same. When you know a little mathematics, okay, I'm not going to discuss that. Okay, if you know it, that's fine. If you do not know it, then also fine. If you apply a little bit of mathematics, you will see that these two are actually same. Okay, so that's it. So your options can be given in this form also. So you have to be careful. Okay, if you got this answer, you don't have to panic. Okay, you try the other approach, then you will get the correct form. Okay, both are actually same. There is absolutely no difference. Okay, you got it. So now we did these two. Okay, now the next one should be simple. Okay, very simple. All are simple provided you do it correctly. Okay. Now the next one. Okay, here we have two radioactive elements, X1 and X2. Half-life 20 days, 10 days respectively. Initial amounts are given 40 gram and 160 gram respectively. Then after how many days both will have same amount. Okay, so you see it is like n is equal to n naught e n naught half power n. Okay, n is the number of half-lives. Okay, After what time? So both start at same time. At t is equal to 0. At t is equal to 0, this x1 has 40 gram, x2 160 gram. Same amount, different amount, but they have different half-lives also. They start together at t is equal to 0. After some time, after some few days, okay, after some time, at some instant, okay, they are going to have equal amount. I have to find that time, okay. I will write like this, okay. I will write like this. It is 40 gram, okay. So 40 and half power t over half-life. What is the half-life? Half-life is 20 days for the first sample, okay, is equal to 160 and half power t over 10. That's it. You just have to solve it and you get the answer. Very simple problem, okay. It should not be a big deal for you, okay. So this becomes 1 over 4 half power t over 20 is half power t over 10. Okay, that's it. This I can rearrange. I can write it as half square and half t over 20 is half t over 10. Okay. So this I can write as half t over 20 plus 2. Both powers get added. Okay. And half t over 10. And that's it. I can just equate the powers to get the answer. Okay. So t over 10 is equal to t over 20 plus 2. Okay. When you rearrange it, you get t over 20 is 2. You get t is 40 days. This is in days. This also will be in days. After 40 days, this becomes from 40 to, it becomes 20 and 10. This will become 10 grams. Half-life is 20 days. After 20 days, it becomes half, 20. After next 20 days, further it becomes half. So from 20, it becomes 10. Now here, half-life is 10 days. Okay, so there will be 4 half-lives. So 160 to 160 to 80, 40, 20, 10. After 40 days, both are going to have equal amount. Okay, that's it. That's how we solve it. Now, next one. What do you think? Okay. Oh. A very, very interesting way of measuring blood. How much blood do I have? To measure that, do I really have to take out all the blood and then measure it and then put it back in my body? We have this interesting ingenious way of doing this. Okay. What we are doing is I have some medicine, some radioactive medicine. Okay. So I fill up that medicine in a syringe and then I inject it into some patient, let's say. The moment I inject it, okay, so I have some amount, okay. The moment I injected it, at that time, its activity was this. The moment I injected, its activity was this. Now, what I'm doing is 24 hours later, I'm taking a 1 milligram sample, 1 ml sample. Okay, 24 hours later, 1 ml blood sample. So I'm taking 1 ml. Okay, so in 24 hours, this radioactive material is going to be like uniformly distributed throughout the body, throughout the blood. Okay, so it is going to have uniform concentration everywhere. Okay, so if I take this blood sample, it is going to have some concentration of that medicine. The same concentration will be everywhere. Okay, so I'm taking this 1 ml blood sample from the patient and then I measure its activity. I find it to be 5 becquerel. 5 becquerel, that is 5 decays per second. And what is the blood? What is the total blood amount of blood in patient body? Can you find it? Did you get the answer? Okay, let's see. Forget about this, all this data here. You see, if the medicine, half-life of the medicine is given 6 hours. Half-life of the medicine is given 6 hours. After 6 hours, what will be activity? Okay, if I do not inject it into the blood, then what will be activity? It is going to decrease. Okay, so activity is equal to A naught, okay, half and power n, okay, number of half-lives. This is going to be equal to a naught is given 4 into 10 power 5, and this is half power. It is 24 hours later. So number of half-lives 24 over 4 over 6. 6 is half-life here. So this is the number of half-lives. So 4. Okay, so 16. Okay, so 4 into 10 power 5 over 16. 2 power 4 is 16. Okay, so this is like 0.25 into 10 power 5 becquerel. What it is? This should be the total activity. Okay, now activity of 1 ml blood is equal to 5 becquerel. Okay. Let's say there is x ml blood. Okay, so if the activity of 1 ml blood is given 5 ml, okay, then what should be the total activity if I take out all the blood? If I take out all the blood, then what should be activity? It should be equal to this, because in all of the blood this whole thing is present. Then the medicine is present throughout in all the blood. Okay, so the activity of all blood should be equal to this. Okay, so I will simply write like this. So x times 5 is equal to 0.25 into 10 power 5. Okay, that's it. Okay, so this is 0.05. X is 0.05 into 10 power 5 ml. This is in milliliter. Okay. So this will be equal to 5 and 5000 ml. This is 5 liters. The patient has 5 liters of blood. See what an ingenious way of measuring blood in your body. Okay, and this is actually done. Okay, these things are actually done. It's not that it's just a theoretical problem. Okay. It has practical uses. And then let's do this last problem and then we will conclude. Okay, last problem. Do you know what is the age of this rock? It is known as dating, radioactive dating. Okay. How do I do radioactive dating? Okay. Let's solve this problem and then we will try to discuss a little bit more about this radioactive dating. One very common method is carbon dating. Carbon C14 dating. C14 dating. Okay. Now, okay. Let's first solve it. So I have this X decaying into Y. Okay. So this is X. It decays into Y. It decays into Y. Now, Y is stable. There is no further decay. There is no further decay. Half-life of this decay process has a half-life of 2500 years. Okay. Now, so in a rock sample, X and Y are found in the ratio 1:7. What is age of the rock? So initially at t is equal to 0, okay. What is the amount of X? Amount of X is n naught, let's say, and this is 0. In the beginning there is only X. Let's say n naught nuclei. With time it is decaying. It is decaying into Y. X decays into Y. Okay, so in the rock sample, the amount of X will keep on decreasing and amount of Y will keep on increasing. Okay, it will keep on increasing. Okay, and at some time when the sample is analyzed, it is found to be in ratio 1:7. Okay, so at t is equal to t. Okay, this is in the ratio 1:7. Okay, that means this becomes n naught over 8 and this becomes 7 n naught over 8. Okay, I have to find what is this time. Okay, now it should be easy. Okay, I will write like this. N is n naught half power n. Okay, so n naught over 8 is n naught half power n. Okay, this is like half power 3 is half power n. N is 3. Okay, so T over T half is equal to 3. So time is 3 half times. Okay, this will be 7500 years. That's how we measure the age of ancient objects, rock samples, or some archaeological evidence and all that. Okay, you must have read these things. We find some bone sample, human bone, and then scientists actually are able to find the age, how old that bone is, that bone sample is. How do they do it? It is known as carbon dating. Okay, carbon dating. Carbon has different isotopes, 12, 13, 14. 14 is radioactive. It is not stable. It decays. Okay, now I am a living person. You are a living person. As long as you are living, okay, you are breathing the air. In air, we are taking in C14. Okay, so in any given sample, okay, the isotopes are present in some ratio. Okay, so when I am taking in food, that food has carbon. Now in carbon, it will have some certain fraction of C12, certain C13, certain C14, and that is fixed. We already know what is the average distribution of C14 in the food we take, the air we breathe. Okay, so that gets absorbed in our body. Okay, so in our body we have like sugar, carbohydrates. They are made up of these carbon atoms. Okay, so there is certain fixed amount of C14 in our body. Okay, and its amount is maintained because as long as we live, we keep on eating food, breathing air, and all that. Okay, so there is always a certain fixed amount of C14 in my body as long as I live, and we know that. Scientists know that in a living person, what is the amount of C14? Now, the moment person dies, then all the processes stop. There is no further intake. There is no intake. There is no input. Now, whatever C14 was present at the time of death, that it starts to decay. Okay, and after some time, if we analyze the sample, we are going to find. So this will decay into some, so it's like this, X is decaying into Y, so C14 decaying into some element. Okay, we already the scientists know all the processes. Okay, C14 is going to decay into what? Okay, so as long as I live, I have certain amount. The moment I die, this starts to decay. After certain time, this and the the daughter nuclei are going to be in certain ratio. Okay, so if I know the ratio, I can find the age. You see, if I know the ratio, the same way that we calculated here. So if I know the ratio of C14, even if not the ratio, even if I know the amount, what amount of C14 is present, okay, then I can find the age using these calculations. That is known as carbon dating. A very useful tool, archaeological tool, very useful. Okay. So that's it. That's it for this lecture, and that's it for this chapter. Also, you do your problems from the problem sheet, and then let's discuss it. Okay, whatever difficulty you face, we are going to discuss it.